There you go.
Thank you. So the last set of lectures before we go on to all the case studies deals with thermal shock theory. And we went over a quick definition of thermal shock, and we started to look at thermal stresses last time. And we got through thermal expansion mismatches for uh, micro stresses due to thermal expansion mismatches as a function of crystal directions or crystal types. And that kind of mismatch led to microcrack formation. The other type of thermal stresses is on the macro scale due to thermal gradients. So we'll go over temperature gradients, and then we'll look at two theories for thermal shock, the thermoelastic theory and the damage resistance theory. The thermoelastic theory is really for advanced ceramics where you want to avoid any kind of damage during a thermal shock. And the damage resistance theory is what really applies to refractories, where you allow damage to take place, but you can control the damage. And I don't know if we'll get this far, but the last section deals with application to refractories, the fracture parameters, how you design process zones. We'll revisit R curves, and we'll look at slow crack growth and a few measurement techniques. So macro stresses are a result of thermal stresses from temperature gradients. So thermal gradients create stresses in a material on the macrostructural level. And that's simply because the free expansion of the different volume elements cannot occur in these thermal gradients. So we'll look at two types of thermal gradients, one due to a very rapid quench, and then one as a result of a gradual quench. So if I were designing a refractory for improved thermal shock resistance, I would use the rapid quench situation because that's the worst possible condition for thermal shock. I can improve the thermal shock of a material under rapid quench conditions, it's going to be also improved under gradual quench. So quenching, you can compare cooling during quenching to the opposite, heating. So when you cool or quench a refractory or a ceramic, the surface is contracting, the interior is not contracting. So that puts a tensile stress on the surface. If you heat a ceramic or refractory, the surface is expanding relative to the interior. So that puts a compressive stress on the surface. So ceramics, refractories, their tensile strength is much less than their compressive strength. That's usually by a factor of 5 to 10. So it's a big difference. So when you thermally shock a material by quenching in the cooling mode, that's going to create much more damage than if you heat a refractory and try to damage it. So that's why basically all of the thermal shock tests are done in the cooling mode because that's the most severe. But damage can also occur in heating. So let's look at thermal stresses when we have a very rapid quench condition. And we'll look at a large plate and basically an infinite plate in the X and Y directions, and it has some thickness, finite thickness in the Z direction. So it's infinite in the X and Y directions. And we rapidly quench it. So the initial temperature is T high, and then we quench it to a lower temperature, T low. So right on the surface, this is the temperature profile. The interior is still at T high, but the surface has dropped to T low. and it's just right at the surface. So we make an assumption that the average temperature of this plate is constant, and we're just altering the temperature at the very surface very quickly. So when we talked about elasticity, I gave the strain matrix, looks something like this. So if we take a cube on the surface in the X, Y, and Z directions and add to it A delta T, the expansion coefficient, times the temperature difference, T high minus T low, that's our strain from the quenching, from the thermal expansion. So as a review, epsilon XX is a strain in the X direction on a plane that's perpendicular to the X-axis. So this horizontal plane here. Sigma XX is the stress in the X direction on a plane perpendicular to the X-axis. So the stress in the X direction on this same plane. So nu again is Poisson's ratio, E is Young's elastic modulus, and delta T is T high minus T low. So the plate has a finite thickness in the Z direction. So there's no restriction in the Z direction. So the stress in the sigma ZZ equals 0. We have restrictions in the Y, X, and Y directions. The interior keeps the surface from contracting. So the strain epsilon XX, epsilon YY are both equal to 0, but we develop stresses on the surface. So sigma XX equals sigma YY equals sigma. So we take any one of these equations and we put in sigma ZZ equals to 0, epsilon XX and epsilon YY equals 0, and put sigma XX and sigma YY equals sigma, and we come up with this equation here, which we can solve in terms of delta T. So if we know the strength of the material, Poisson's ratio, its elastic modulus, and its thermal expansion coefficient A, we can calculate the delta T, and that's the delta T where fracture will take place, assuming we put in the fracture stress sigma. So I've calculated that for 3 different types of materials: a soda lime silicate glass, a dense alumina, and then a dense silicon carbide. So the Young's elastic modulus for glass is about 10 million PSI. The strength is about 10,000 PSI. Poisson's ratio is about 0.2. The thermal expansion coefficient is 10 times 10 to the minus 6 per degree C. Putting these values into this equation, we get a delta T of 80 degrees C. So it only takes a change in temperature of 80 degrees C to fracture a soda lime silica glass, which is basically window glass. Dense alumina has a Young's modulus of 50 million PSI. It's stronger than glass, 50,000 PSI. Nu is about 0.2 again. The expansion coefficient is about 8.4 times 10 to the minus 6 per degree C. So putting these numbers into this equation, the delta T is still really low, 93 degrees C. So it only takes a small temperature difference to fracture dense alumina. A silicon carbide has a higher modulus, 60 million PSI, higher strength, 80,000 PSI. Poisson's ratio is about 0.14. The big difference is A here, the thermal expansion coefficient. It's less than half of each one of these for the alumina and the glass. So it's only 4 times 10 to the minus 6. So if you put these values into the same equation, delta T is higher now, 287 degrees in order to cause fracture. So these are all relatively low temperature differences. But you can see the effect here of lowering the thermal expansion coefficient. It really increases that delta T. If this expansion coefficient A is extremely small, this number goes really high. But unfortunately, we're stuck with materials that have some decent amount of thermal expansion. So for the gradual quench conditions, we can have steady state or transient. So they create different types of thermal gradients. So for the steady state gradual quenching, we take another infinite plate and we have a constant cooling or heating rate. So that would be our steady state conditions. So this is a plate of thickness 2 rm. So rm is 1/2 the thickness of the plate. Phi is the constant heating or cooling rate. Ts is the surface temperature. Ti is an interior temperature. And then Ta is the average of the surface and interior temperature. So temperature is increasing in this direction. So we start out with a material at a certain temperature and we cool it at a constant rate. So the surface, outside surface is contracting, so it is put in tension. And when we have constant cooling or heating rates, we have a parabolic temperature gradient. So the crosshatched area here and here between the surface temperature and then the average temperature, that's the portion of the material on the surface that's in tension. And then the interior is going to be in compression. And if we heat it, we're still going to have this parabolic temperature gradient, but now the surface is going to be hotter than the interior. So between the surface temperature and the average temperature, the crosshatched areas on either side represent the part of the surface that's in compression. And now the interior is in tension. So cooling and heating at constant rates produces these parabolic temperature gradients. So we just developed this equation, and we want to calculate the stress during the steady state gradual quenching or cooling. So we just developed sigma equals the elastic modulus times the thermal expansion coefficient times the temperature difference. And this is in biaxial, it's a biaxial stress. So we have a 1 minus nu, 1 minus Poisson's ratio term. So we need to get an expression for delta T, the average temperature minus the surface temperature. So in this large plate, delta T, T average minus T surface, it's going to be given by this expression. So phi is the constant cooling rate. Rm is squared here. Rm is the half the sample thickness. C is a constant, and for a plate, that's 1/2. Now I have to take into account the thermal conductivity K, the density rho, and then the heat capacity. So we substitute delta T into this equation, and we end up with sigma, the strength, equals the elastic modulus times the expansion coefficient times the cooling rate, and Rm is this half the sample dimension, and that's divided by 2 times the thermal conductivity, and that's divided by the density, the heat capacity, and then 1 minus Poisson's ratio. So this equation is for a plate. We're taking this expression for delta T for a plate. We can look at other geometries for delta and have an expression for delta T. So this is just a reference slide. We just considered the infinite slab, and the stresses are going to be of this form with our temperature difference. And then this is for a thin plate, a thin disc, a long solid cylinder, a long hollow cylinder, a solid sphere, and then a hollow sphere. So all different kind of sample shapes. These are the stresses that develop on the surface, and then these are the stresses in the center. So we also have these temperature differences, and then these are the temperature differences for the different shapes. So this would be an infinite plate, an infinite cylinder, a cylinder of a half length. This would be a short cylinder, and then a cube. So these are the delta T's for the different shapes. So we started out with this type of equation for a plate, and then we have the same type of equations for different shapes, and then the delta T's for the different shapes. So what happens in reality, real cases, we don't really want to change the surface temperature infinitely fast. Hopefully we can avoid that. And then the heating and cooling rates are not going to be constant either. So in real cases, hopefully we're not quenching extremely rapidly, and these heating and cooling rates are not going to be constant. So there's going to be a finite time before we reach the maximum stress, where we have our potential damage during thermal shock. So we use a non-dimensional stress, which is the ratio of the actual stress to the stress that would result from this infinitely rapid quench. And for an infinite plate, it looks like this. So sigma star is a non-dimensional stress. And this is the equation that we developed for an extremely rapid quench. Sigma divided by E, the thermal expansion coefficient, delta T, and then 1 minus the Poisson ratio. So with this non-dimensional stress, we have to consider something called BO's ratio. So beta is BO's ratio. It takes into account the sample size, the heat transfer coefficient from the surface, and then the thermal conductivity. Sample size is important. The bigger the sample size, the bigger the thermal gradient. So this is our non-dimensional stress, the stress on the surface relative to a stress for an infinitely fast quench. So that's some fraction from 0 to 1. This plot goes from 0 to 8.8. We plot it against time for different values of beta. So here's beta equals 20. At some point, there's a maximum, and these vertical marks show where that maximum is. So at some time greater than 0, based on a beta equals 20, this would be our maximum stress that's developed, and it's about 0.7 of an infinitely fast quench. And then let's say beta equals 1. It takes a much longer time to reach the maximum stress. And then that maximum stress is only 0.2. So it's 0.2 of the stress you would have if you had an infinitely fast quench. So this top case here, as beta becomes larger and larger, it approaches infinity. That's where the maximum stress occurs at time 0 here. So this would move up towards 1 here. which is this, this only goes to 0.8, but if it was, we had one here, it would be our rapidly quenched material. So as beta approaches infinity, the maximum stress occurs at time zero, and that's basically our rapid quench conditions, which we just discussed a few minutes ago. As beta decreases in this direction, the time to reach this maximum stress increases, so these maximums are moving to the right in longer times. And then the magnitude of the maximum stress is decreasing. So that's how this works with BO's ratio. So beta equals Rm H over K. Rm is related to the sample thickness, half the sample thickness. H is the heat transfer coefficient, and K is the thermal conductivity, which we spent the whole lecture discussing the conductivity. So ceramic refractory materials with low values of H and high thermal conductivities produce less severe temperature gradients. So the slower the heat transfer from the surface, the higher the thermal conductivity, that gives you a lower value of beta and puts you down here where the stresses are lower and they take a longer time to develop. So beta is a function of sample size. So the smaller the sample, the harder it is to develop large temperature gradients. The lower the value of the heat transfer coefficient, the lower the value of beta, and the higher conductivity. The higher the conductivity, the harder it is, again, to develop a steep thermal gradient. So I just put down a table here that shows different values for this term H, the heat transfer coefficient. And there's two units here, BTUs per hour per foot squared per degrees F, or calories per second per square centimeter degree C. So if we have a cylinder and we have air flowing over that cylinder, and in pounds per second per foot squared, going from 0.025 to 2.5, 25, and 60, the heat transfer starts out at 2 and increases to 190. So the higher the flow rate of air past the cylinder, the higher the value of H. If we have a material sitting at 100 degrees, 1,000 degrees C, and we change the temperature, the heat transfer coefficient due to radiation is about 26. If we have a lower temperature, the radiation, the heat transfer due to radiation is about 7. That's radiation in this temperature range under ambient type conditions. If we quench it, we really increase the heat transfer coefficient from maybe 1,000 to 10,000. And a turbine blade that's turning might be 35 to 150. So examples of different heat transfer coefficients under different conditions. So it turns out for refractory ceramics, this sigma star maximum actually is going to be about 0.31 times beta, or 0.31 times RmH over K. So this is the maximum stress for low values of the heat transfer coefficient, which is common radiation conditions. So the common radiation conditions, two examples, were between 0 degrees C and 1,000 and 0 degrees C and 500. These are pretty low compared to, water quenching. So this sigma star, if we make it a maximum at the worst condition, a sigma max is going to be 0.31 times RmH divided by K. So that was a rapid quench situation, quenching at a constant cooling rate, and then taking into account, hopefully we're not quenching extremely rapidly and not at constant rates, how the stresses develop according to VO's ratio. So there's two approaches for designing a ceramic or a refractory material to resist thermal shock. The first is the thermoelastic theory. So this avoids failure, any type of failure, especially catastrophic failure. And you resist initiation of a crack. So you don't want any strength loss after a thermal shock. That approach works for high strength technical type ceramics, dense, fine grain size, very little porosity, very little flaws. The other approach, thermal shock damage resistance, is what applies to our refractory materials. The cracks are always going to initiate, and they're always there. The micro cracks are there. We talked about micro cracks. It's easy to start a micro crack moving. So we can't avoid crack initiation, but what we want to do is to keep that crack from moving, make it really hard for the crack to propagate, and that minimizes the damage. So we allow cracks to grow. We try to stop them from growing, and we minimize the damage. So we allow the refractory to fail or decrease in strength very slowly over a long time period, hopefully. So we'll go over both of these approaches. So for the thermoelastic theory, there's two parameters that are pretty common. These are R parameters. One's for rapid cooling, one's for gradual cooling. So R is for very rapid quenching, and then R prime is for gradual cooling. So for the worst condition, the rapid cooling, we again have our infinite plate. We just developed this equation, delta T equals the stress, 1 minus Poisson's ratio divided by Young's modulus and the thermal expansion coefficient. So we set at failure, when we reach this fracture stress, we have a certain delta T at failure, delta TF. We set delta TF equal to R, and that's our R parameter. So delta TF is the temperature difference that caused fracture, and sigma F is the fracture stress of the material. That's for an infinite plate. Other shapes, there's a shape factor S. So the delta TF just equals R times the shape factor S. So if we have a high performance technical ceramics, again, it'd probably be high strength, very fine grain size microstructure, very little porosity, very few flaws. We want a high R value. So we want to start out with a material that's very strong, a high fracture stress, with a low elastic modulus and a low thermal expansion coefficient. This is not that easy to do for a high performance material, because if you have high fracture strength, you're probably going to have high elastic modulus. They go together. So making this fracture strength in the numerator very high is going to put E in the denominator relatively high. But what this predicts is you need a high strength, low modulus, low thermal expansion material. And again, our thermal expansion coefficient, they're set values for the different kinds of materials. Unfortunately, they're not really extremely low to give you a high delta T. So some examples for R, I just compared a soda lime silica glass again, and I compared it to a fused silica glass. So in both cases, the modulus is about 10 million PSI. Soda lime silica glass again is about 10,000 psi. Fused silica glass is a little stronger, 15,000 psi. They both have a Poisson's ratio of about 0.2, but the big difference is in the thermal expansion coefficient. So for soda lime silica glass, it's 10 times 10 to the minus 6 per degree C, but it's 20 times smaller for fused silica glass. It's only 0.5 times 10 to the minus 6 per degree C. So R, in terms of degrees C, is only 80 degrees C here, but R over here is 2,400 degrees C. Obviously, this is unrealistic because the glass would be no longer solid at this point. It would be molten, but it just shows you how the effect of the thermal expansion coefficient has on this delta F. So a really high number for a very low thermal expansion material. So still on a thermoelastic theory for gradual cooling, we just developed this equation here. The maximum stress, 0.31 times Rm, a sample dimension, H, the heat transfer coefficient, and K, the thermal conductivity. We set that equal to our equation for the maximum stress, sigma F over E, A, delta T, and 1 minus nu. And then we just solve it for our delta T. So our delta T at fracture is a function of the thermal conductivity, the fracture strength, Poisson's ratio, and that's divided by the elastic modulus, the thermal expansion coefficient, and that's times 1 over this term here, 0.31 RmH. So this part of the equation right here is R prime. So now we have a thermal conductivity term in here. We didn't have K in the equation for R, but now for R prime, we incorporate the conductivity. So the higher the conductivity, the higher the R prime value, the better the thermal shock resistance is. And just like for R4 prime, you can do other shapes besides a plate and have a shape factor S. So now for high values of R prime, you want a high fracture strength, high thermal conductivity, low elastic modulus, low thermal expansion. Also, sample size is a factor. The smaller the sample size, the smaller the thermal gradients, and the smaller the heat transfer coefficient. So small sample size and small heat transfer coefficient give a high delta T for fracture. So the thermoelastic theory gives you a temperature difference where the fracture initiation takes place. And if you have a high strength material, when you initiate fracture, you're probably going to have a catastrophic failure. So you want that delta T to be as high as possible in these technical high performance ceramics to avoid a catastrophic failure. But you can't design a refractory like that because of the microstructure is so heterogeneous. It's already flawed with microcracks and porosity. So you have to use a thermal shock damage resistance theory. So there's two common parameters, RST and R4 prime. They're both for extremely fast cooling conditions, rapid cooling. So when you design a refractory microstructure to resist thermal shock, you design it to minimize the thermal shock damage. You can't design it to avoid damage, you have to minimize it. So thermal shock crack initiation is going to take place. You can't avoid that, but you want to minimize the damage. So it's impossible to design a refracting microstructure to avoid thermal shock crack initiation because of the high density of flaws already in the material. So we mentioned stored elastic strain energy. That's the driving force for crack propagation. So energy is dissipated when we form the crack. So the stored elastic strain energy is converted to fracture surface energy. So the model in this theory is shown here. We have a body of dimension D at a temperature T1, which is higher than the second diagram here, which is T2. So T1 is greater than T2. The body has the same dimensions. The red cross hatching just means we're restricting this body from contracting when we lower the temperature. So this body has N cracks per unit volume. So there's N microcracks per unit volume. So we start out at dimension D, we cool it from T1 to T2, but we don't allow it to contract. We constrain it in all three directions, so it's a triaxial stress state. So we maintain its dimension D at the lower temperature. So under rapid quenching conditions, that will develop the maximum stresses on that body. So sigma equals the Young's elastic modulus times the thermal expansion coefficient times the temperature difference, T1 minus T2, and now it's 1 minus 2 Poisson's ratio because it's a triaxial stress state. The biaxial stress state on the flat plate was 1 minus nu. So sigma equals EA delta T divided by 1 minus 2 nu. So constraining that in three directions is the worst possible condition of thermal stress because we prevent it from shrinking during the temperature change. So that's the worst possible condition for thermal shock. And then there's an energy balance approach to describe this. So for crack stability, the total energy per unit volume has to equal SE. SE is the stored elastic strain energy. That's the elastic strain energy due to the thermal stress field from the change in temperature, plus the surface. So U surface is the crack surface energy. So in this model, this equation is for U total. So I'm just going to show the key parts of this derivation. So this first term here is a stored elastic strain energy. This part of the equation is the correction in the strain elastic strain energy for cracks that are present. It lowers the stored elastic strain energy. And then this last term here is our surface energy term. So this first part here is U SE, and the last part here is U surface. So what's in this equation is the thermal expansion coefficient, the temperature difference. E0 is the Young's elastic modulus without any cracks present. Nu again is Poisson's ratio. This Poisson's ratio again. N is our crack density. L is the crack length, the crack size. Poisson's ratio appears again. And then N again is the crack density. L is the crack length. And now we have our gamma F, which is our fracture surface energy. So the stored elastic strain energy is converted to fracture surface energy. And when we looked at the Griffith equation, we took the derivative of the total energy with respect to crack length, set it equal to 0, and that was our point of instability. So that's the point where the cracks start to grow or propagate. So we do the same thing for this equation, we differentiate it with respect to L, and then we solve it for delta Tc, the critical temperature difference for crack propagation. So we have our fracture surface energy, our Poisson's ratio, our elastic modulus for a crack-free material, the thermal expansion coefficient. Poisson's ratio appears again and again. Our crack density, our crack length, and again, Poisson's ratio and another term for the crack length. So if we plot, this is delta T versus crack length. And this is actually the half crack length. So this delta T critical goes through a minimum. So there's a region of instability. It's bounded by two values of crack length. So here's our region of instability, and then below that is our region of stability. So the delta Tc goes through a minimum, and N is the different crack density. So N is 100, 10, and 1. So the solid line is a critical temperature difference for initiation of the crack movement or crack propagation. If the crack is initially very short, there's some excess kinetic energy. So the crack doesn't stop when it reaches this region of stability. It continues to grow a certain distance, and that's given by this dotted line. So this dotted line would be for N equals 100. This is for N equals 10, and then this one's for N equals 1. So how this works, let's look at a crack 1 here. So let's say region 1 is to the left. We're to the left of this minimum. So that means we're going to start out with the refracting material with cracks present, but they're going to be relatively short. And on this diagram, this minimum is about 10 to the minus 1 centimeters. So this crack is over here. So when actually, I'll show it in more detail in terms of delta T, but we have a short crack. It grows when we reach a critical delta T, but it doesn't stop here. It has excess kinetic energy. So it propagates a certain distance, and that looks like about 1 centimeter here. And then it arrests at this dotted line, hopefully. So if it's a well-designed refractory with small cracks, it's usually going to arrest and you won't have any catastrophic failure. So again, region 1, we're to the left of this minimum. It's a short crack. It has excess kinetic energy when it propagates. It doesn't stop here in the region of stability, but it continues to propagate till all excess energy is dissipated. If we're in region 2, we're to the right of this minimum. So we have a material with a much longer crack. So when we reach our critical delta T, that crack stops propagating. It arrests right here and then continues to follow this curve. So that's quasi-static crack propagation, and no chance of catastrophic failure there. So those are the two possibilities: short cracks, long cracks. So for initially short cracks, this is our equation for delta T and delta Tc actually. So this part of the equation, if we have very short cracks, this part right here, which is over here, is going to be much less than 1. So we can ignore this part for short cracks. So delta Tc just equals this equation here. It's simplified by eliminating this portion. So this is delta TC to the left of the minimum point. And then if our cracks are very long, now this term here, same term, is much greater than 1. So we eliminate the 1 here. And then we simplify this equation by eliminating the 1 here. This is our delta TC. So this describes the region to the right of the minimum point. And now we have the crack density here. Here we don't have the crack density, we have the crack length. This one has both the density and the length. So delta TC in region 1, and then delta TC in region 2. So we mentioned that in region 1, where we have these short cracks, the crack doesn't arrest, it continues to grow somewhat. So we needed additional criteria to describe that crack propagation. So where it should stabilize, right here, it continues to grow somewhat. So the strain energy release rate at that point is greater than the creation of fracture surface energy. So here's our crack. So we have high strain energy and low surface energy. And then we allow it grows, it's allowed to grow into that region of stability. So now we have low strain energy and high fracture surface energy, which decreases the elastic modulus. Anytime you create microcracks, you decrease E. And again, this is under constant strain. We're not allowing this cube shape here to contract. So region 1, the excess strain energy is transformed into kinetic energy of this crack. So we have, at this point, we have excess kinetic energy, and it propagates until we reach this point where the strain energy that's present at this point is converted to the fracture surface energy. So we have to balance the energy for the entire crack growth process. So now we're adding an initial crack length L0 over here. We're basically just expanding the equation that we use by adding an initial crack length, a final crack length, and also here for the fracture surface energy portion, we're putting a final minus an initial crack length. So L0 is the initial crack size, LF is the final crack size. So short cracks, LF is much greater than L0. So LF reduces to this equation here. So the final crack length is a function of the initial crack length and the crack density. If we assume we have a penny-shaped crack, which is quite common in fracture mechanics, this is the fracture strength for initial crack of length L0. And then we solve for LF by substituting in L0. And we end up with an equation that gives us our final crack length for region 1. We have our Poisson's ratio, our fracture stress, crack density, our fracture surface energy, and the Young's modulus. That crack that's growing into the region of stability has an area A. If it's a penny-shaped crack, it's pi LF squared. So we can define our area in terms of pi LF. So the area is proportional to the fracture surface energy times the modulus divided by the strength squared, 1 minus 2 nu. So from this equation, we can split out R4 prime, which is what we were trying to get at. This part of the equation right here. So R4 prime is a function of the fracture surface energy, the modulus, the strength, and Poisson's ratio. So this is one parameter, and R4 prime applies to the left of the minimum in that curve, and the delta TC versus flaw size curve where we have short cracks. So if we want to avoid a catastrophic failure during our most severe thermal shock condition, the rapid quench condition, we need a material with a high R4 prime value, a high fracture strength, a low elastic modulus, and a low strain. So these are achievable. You can lower the strength of a material quite easily by introducing micro cracks. And you can play with the microstructure, and we'll go over this in more detail, to increase this fracture surface energy. We're going to go over three kinds of fracture surface energies. We won't have time today, but we'll finish up this section next week. There's a fracture surface energy based on thermodynamics. There's a fracture surface energy to initiate a crack, and then there's a fracture surface energy to propagate the crack. This is the fracture surface energy to propagate a crack. You can change the microstructure to really improve that. So that's R4 prime, rapid quench conditions, small initial crack size to the left of the minimum. And then if we start out with long cracks to the right of the minimum, our delta TC is given by this equation, and it's proportional to the fracture surface energy again, but it's now divided by the thermal expansion coefficient squared and the Young's modulus. And that's the square root of this term. So we pull out this term from this equation. That's RST, the stability crack stability factor. So that just equals gamma F over A squared E0 to the 1/2 power. So that's starting out with long cracks. We're having quasi-static crack propagation under rapid quench conditions. So to make a high value of RST, you need a high fracture surface energy, a low modulus, and a low thermal expansion. So you can use R4 prime and RST, and you see the terms in here: fracture surface energy, elastic modulus, strength, fracture surface energy, thermal expansion coefficient, and Young's modulus. So you can manipulate those different factors to try to increase R4 prime and RST. And that's the real secret to developing refractories with high thermal shock resistance, is to maximize R4 prime or RST. And when we go over the case studies, we'll look at a lot of cases where people have manipulated the microstructure and maximize these parameters. So what's actually happening during crack growth? So we have our delta T versus our crack length. Here's our region of instability, and here's our region below that of stability. So let's say we start out with a crack length to the left of this minimum. So this is somewhere between 10 to the -2 and 10 to the -3 centimeters. So we increase the delta T. So we keep increasing delta T. We're in the region of stability, nothing happens. And then we reach this boundary here. As soon as we reach the region of instability, this crack propagates. It goes past this curve here because it has excess kinetic energy and is eventually arrested. At this point, the excess kinetic energy is converted to fracture surface energy, and the crack stops at that dotted line. So this is the case where n equals 100. So then we have to increase the delta t again, but nothing happens. The crack size stays the same. We keep increasing delta t until we reach the region of instability again. At this point, we have crack growth taking place again, and this is a quasi-static crack growth. So it's very slow, controlled crack growth. So this is the path that the fracture takes place as we increase delta t. So once we reach this point, we can keep increasing delta t and we have quasi-static crack growth. It's a slow, stable crack growth. This is how you want to design a refractory material. So we can just reverse the axes and move crack length from the horizontal to the vertical axis, and then move temperature difference delta t from the vertical to the horizontal axis. So we have an initial crack L0. We increase it to a critical delta t. That crack immediately grows. We have some kinetic crack propagation. The crack length stops. We then have to increase it to the second critical delta t right here, and then the crack starts growing in this quasi-static manner. So A, we have no fracture taking place, no growth in the cracks. We have some kinetic crack growth at a critical delta t, then no change in crack length again until we reach the second critical delta t, and then we have our controlled crack growth, this quasi-static crack growth. So in the lab, if you want to do an experiment where you subject samples to different delta t's, trying to figure out and measure in these materials the crack length is very difficult. But strength is proportional to crack length. We know that from the Griffith equation. So in the lab, we can measure strength versus delta t. So we start out with some initial strength S0, and that corresponds to an initial crack length L0. So we keep increasing the delta t, so we have no change in strength. Then at some point, we reach this critical delta C, and we have a drop in strength. And then we have to keep increasing the temperature to delta T, second critical delta T. So there's no change in strength until we reach that second critical delta T. And then we have our quasi-static crack growth and a gradual decrease in strength. So ideally, you want to avoid this drop in strength. You want this dotted line to come up here. So you always want a gradual strength decrease in a refractory material. Depending on the crack size, you may have this kind of behavior, or you just may have quasi-static crack growth. So we developed an equation for R, R4 prime, and RST. So that's what you should get out of this lecture. And you can't maximize both resistance to fracture initiation and resistance to crack propagation. So R is for fracture initiation. So once you reach this delta TC, you're most likely going to have a catastrophic failure. R4 prime is for kinetic crack propagation, short cracks. And that was our equation for R4 prime. And then longer cracks, we have quasi-static crack propagation. That's RST. So if we look at R compared to R4 prime, R is proportional to the strength over E, so sigma F over E. And then R4 prime is basically the opposite. It's E over the stress squared. So we have E over sigma F. Here, strength is in the numerator. Here it's in the denominator. Here, modulus is in the denominator. Here it's in the numerator. So these are complete opposites. So it's not possible to design a refractory material to resist crack propagation and crack initiation. And it's not possible to design a high-strength technical ceramic to resist catastrophic failure and to have a high resist crack propagation. So R and RST show you the difference between the two types of materials. So we use R4 prime for refractories. So if you measure strength as a function of temperature, you can get graphs that look like this. This is what the theory predicts, and it predicts what happens in actual use. So this is strength versus temperature for four materials of different grain size. So the small grain size material, 10 microns, is down here. The coarser material, 85 microns, is up here. So this is what you want to have for a refractory. They have low strength, less than 5,000 PSI. This is what happens to an advanced technical ceramic that's high strength, greater than 50,000 PSI. So in the top case here with the coarsest microstructure, the biggest grain size, you reach a critical delta T of around 200, and then you have quasi-static crack propagation and this gradual strength loss. So this is the ideal type of strength loss you want for a low strength refractory. The other extreme is a high strength material, and you reach this critical delta T and you have a large drop in strength. This one could be catastrophic. It would go to zero, but it does arrest. And then you have to reach a second critical delta T to continue the crack growth. And then two different other sizes, 34 and 40 microns, they have behavior in between. So the theory where we develop R4 prime and RST actually works in reality, and you can use that to develop thermal shock resistant materials. I have enough time to compare RST and R4 prime. This is RST, this is R4 prime. And the thermal elastic stress, and we've had total linear restraint. Sigma F equals A, E, and then some function of temperature. So if we square this, the strength squared approximately equals the expansion coefficient squared, the modulus squared. Or if we divide by E, it's sigma F squared divided by E, which is approximately for sigma F squared, A squared over E zero. So we take this sigma squared E zero and we substitute that in for A squared E zero, which is right here in RST. So now we just rewrite RST in terms of the fracture energy, the modulus, and then the fracture strength squared. So if we look at RST and R, we both are, after we divide by E, both are proportional to 1 over sigma F squared E zero. So they both have the same general dependence on strength and Young's elastic modulus. So a lower strength, higher modulus material gives a higher RST and higher R4 prime. This term, sigma F over E zero, is a version of the stored elastic strain energy. And so by going to low strength and high modulus, you minimize the stored elastic strain energy. So you design refractory materials that have low stored elastic strain energy which maximizes RST and R4 prime. So the stored elastic energy term, we went over this, work divided by volume. So U is the stored elastic strain energy per unit volume. That just equals 1/2 stress times the strain. And sigma is the normal stress, epsilon is the normal strain. The stored elastic strain energy has units calories per cubic centimeter or perhaps joules per cubic meter. And this is the driving force for fracture. So you want to minimize that by controlling the microstructure. And we showed that U is just the area of this triangle under the stress strain curve, and it just equals 1/2 sigma epsilon. And 1/2 sigma epsilon, using this expression, sigma equals epsilon E, we can write the stored elastic strain energy in terms of sigma squared and E, which is what I did over here. It's just a different version. So by comparing RST and R4 prime, they're both proportional 1 over this stored elastic strain energy term, sigma F squared over E0. So again, you maximize either one of these parameters by minimizing the stored elastic strain energy. And you can do that by reducing the strength, lower stored elastic strain energy, give rise to a higher RST and R4 prime. So you lower the strength by putting in large flaws. One way of doing that is putting in large aggregates that have expansion mismatches with the matrix, or putting in pores. All of these are large flaws, make the strength lower, makes this term lower, increases these values. So the ideal refractory design, well, you want to start at the minimum in these curves as a function of your crack density. So if you start at the minimum in this delta T versus crack length plot, and you put yourself at this point, you have quasi-static crack growth. You don't have any kinetic crack growth. So depending on your crack density, wherever these minimums are, that's where you want to start your ideal microstructure. So for refractory design, you start at the minimum in the delta T versus crack length plot L. The grain size controls flaw size. The population of pores and microcracks is very inhomogeneous. So the pore population, the microcrack population, and the size of the pores and microcracks is also going to control the number of cracks. So you control the flaw size, the flaw population, to try to put yourself at these minimums in these curves. And let me see. I think I'll stop right there today. We just have a little bit to finish up on RST and R4 prime. And then the last thing I want to talk about is kind of tying this all together. We talked about fracture toughness. We talked about strain energy release rate. We didn't talk about gamma NBT, the fracture surface energy to initiate a crack movement. We'll talk about that. And I'll introduce a concept called the J integral. Gamma WF is the fracture surface energy to propagate a crack. So we'll compare gamma NBT and gamma WF, and we'll revisit our curves. So these are linear elastic fracture mechanics parameters. These are nonlinear elastic. So hopefully next time, we don't have that much more to go, but we'll tie all this together, and we'll finish up on our R4 prime and RST and tie it all together. And we should be able to finish that out next Tuesday, and we'll start on case studies. And the first group is alumina silica refractories. So we'll start out with 100% silica refractory, and then we'll look at higher content aluminum materials from fire clays to mullite to high aluminates. So that's where we'll stop today. And again, thanks for listening, and have a good weekend. I think it's a 3-day weekend for most everybody with the holiday, and we'll see you next Tuesday. Thanks again.